Our earliest efforts to harness the fundamentals of nature have already changed the world. Microprocessors, global positioning systems, mobile phones, internet communications, non-invasive medical imaging, all work because of our understanding of quantum physics. But these represent only the most rudimentary control over the quantum world. The future of research in quantum physics is promising new applications we can only barely imagine today. In laboratories like mine all over the world, we're learning to control matter at the most fundamental levels. By taking control over matter, we're ushering in the development of a new generation of technologies based on access to quantum physics, quantum tech. Instead of taking what nature gives us, we are taking control of nature, sometimes engineering matter atom by atom. When we do this, we gain access to a host of exotic new phenomena because the world on these tiny scales is governed by the rules of quantum physics. When we peer deeply into matter, not just at the scales smaller than a human hair or thousands of times smaller, but millions of times smaller than a human hair, when we can see single atoms, or even inside those atoms, the familiar laws of physics give way to strange new rules. At these tiny size scales, little that you and I perceive persists. Quantum particles, like atoms and electrons, behave more like waves than particles, or billiard balls. They can exist in superpositions, such they could be in more than one state at once, and they don't choose one or the other until we measure them. Nature at these scales even possesses its own form of magic. Entanglement allows two particles to be inextricably linked no matter how far apart they're separated. Manipulating one instantly affects its partner. But today's technologies completely gloss over this phenomenology. For years, these phenomena were derided by the greatest scientific minds of the 20th century, with even Einstein dismissing the notion of entanglement as spooky action at a distance. But these are no longer perceived of as mathematical oddities. They are real and accessible in the laboratory today. We can control and manipulate these phenomena and demonstrate that the quantum models we have of reality are correct. No other model can match our observations. Today, with our growing control over matter, we're looking to exploit these phenomena as resources, powering a new generation of technologies much the way we use the flow of electricity to power our technology today. This is where my personal story intersects. I'm an academic physicist. I run a research group of many young men and women, scientists and engineers working to bring quantum tech to reality. My team is focused on experiments using trapped atoms. We can confine them in special electromagnetic bottles called ion traps, and then use them to understand how we can coax quantum systems into performing useful tasks. Our research takes inspiration from the advent of modern aviation. Early in the development of flight, great pioneering thinkers learned that by exerting exquisite levels of control over their hardware, they could overcome the fundamental barriers in the field. Likewise, by combining concepts from quantum physics and control engineering, we're learning how to overcome the fundamental barriers standing between us and the quantum future. I'm in Sydney pursuing this research because Australia has long been at the forefront of this field. I was born and educated in the United States and moved to Australia in 2010 to establish a research group and join the growing community of scientists pushing forward on quantum tech. Today, I'm a chief investigator in the ARC Center of Excellence for Engineered Quantum Systems and one of 5 faculty members at the University of Sydney focused on quantum tech. Of course, we're not alone in this research endeavor. We have partnerships internationally with top academic institutions, industrial partners, and global governments all over the world. In fact, my research lab is more than 50% funded by the United States government. This relationship between Australian researchers and US intelligence agencies has existed since the dawn of the field in the 1990s, and today supports literally dozens of scientists across Australia, including all of my peers at the University of Sydney. This relationship persists because it is widely recognized that the potential for quantum tech to change the world is real and now within reach. But our interest is not only in applications for intelligence. Instead, we're working to underpin a new blossoming of innovation based on access to quantum tech. Of course, these are not experiments that you can easily do in a teenager's bedroom. They require access to exquisite research infrastructure, like that available in the Sydney Nanoscience Hub at the University of Sydney, recently completed, which gives us access to some of the most precisely controlled laboratory environments anywhere on Earth. By and large, across the innovation ecosystem, only universities are making this kind of capital-intensive investment in research infrastructure. But supporting quantum tech and quantum innovation also requires an understanding and appreciation of separation of timescales in research. We need scientists and technologists to pour their creativity into overcoming some of the greatest challenges in the field. Problems that may take decades to overcome and may not yield a single commercial outcome in their lifetimes. Simultaneously, we need industrial partners to help teach us how the discoveries coming out of our laboratories can be turned into marketable products. And we need innovators and entrepreneurs excited by the prospects that quantum tech brings, looking to build new technologies and capabilities for the future. Without any one of these, innovation in quantum tech falls apart. At the University of Sydney, we're not only interested in building quantum tech, we're working to build the ecosystem of innovators and entrepreneurs trained in this discipline and able to take today's laboratory discoveries and turn them into the technology of the future. As our mastery of matter expands and quantum tech matures, the extraordinary requirements we have on our laboratories will gradually diminish. And quantum tech will one day be as ubiquitous in a hacker's bedroom or in a roboticist's lab as mobile phones are today. Quantum tech is poised to be, to the 21st century of innovation, what computers were to the 20th. I'd like to now tell you a little bit about one of the applications we're developing, called quantum simulation, a topic my group is working on. Again, we take inspiration from the development of modern aviation, where for years engineers would build scale models of aircraft and test their properties in wind tunnels. We're now building quantum scale models of exotic materials and chemicals in order to gain new insights into the underlying phenomena. By gaining these new insights with our quantum scale models, we're working to bend those phenomena to our will. As an example of the kind of problem we think we can solve, consider superconductivity, in which electricity can flow in certain materials with no resistance. Despite many decades of research, one class of superconductors, known as high-temperature superconductors, remain poorly understood. And this is by and large because the underlying phenomena come from quantum physics, which is notoriously difficult to simulate on a conventional computer. By building a quantum scale model that mimics the material of interest in our quantum simulators, we think we may be able to crack this problem. And if we can do that, the outcomes are extraordinary. Imagine the ability to transmit energy over vast distances with nearly no loss. The modern information revolution came about in large part because of our ability to transmit data over huge distances with nearly no loss in fiber optics. Can we imagine something equally profound happening if we achieve the same with energy? Or consider major problems in industrial chemistry. Recently, a team of scientists in Switzerland posited that with a small-scale quantum simulator consisting of just about 400 elementary units, it may be possible to make a breakthrough in the development of techniques for the production of agricultural fertilizer. The current process is nearly 120 years old and consumes nearly 5% of total annual natural gas production globally. It's because it's so extraordinarily inefficient. By building a quantum scale model of this problem, we may be able to develop a new catalyst to overcome this efficiency barrier and support the generation of new forms of agricultural fertilizer and a host of other chemicals. And just for a minute, think what might happen if both of these projects come to fruition. Imagine the ability to build wind farms in the ocean, or solar farms in the middle of the desert, and pipe energy over thousands of kilometers to cities on the coast. Imagine the ability to hook up the most remote regions of the globe to an energy superhighway the way we hook up remote communities to an information superhighway. With abundant agricultural fertilizer and access to clean energy, we can take parched lands and make them arable farms. We can realize the science fiction dream of terraforming. Now, these are exceptionally ambitious goals, so much so that they may not have much more than the slightest hope of success. Even if we can learn how high-temperature superconductors work, we may not be able to translate those scientific goals into the technological outcomes and power distribution that I told you about today. But I want to leave you with one thought. In the history of innovation, we have seen over and over again that the most profound impacts of new technologies are those that were least anticipated. Quantum tech is poised to deliver new capabilities unlike nearly anything that's come before and to radically transform our world. I'm very excited to be part of that journey and to share our story with all of you today. Thank you very much.